Propagation of uncertainties. Sure, I'd be happy to explain more about the propagation of uncertainties using significant figures. When you perform a calculation that involves measured values, the uncertainty in the final result depends on the uncertainties in the measured values. The uncertainties in the measured values can arise from various sources, such as limitations of the measurement device, human error in reading the device, or variability in the physical system being measured. To account for these uncertainties, scientists and engineers use a technique called error propagation, which involves calculating the uncertainty in the final result based on the uncertainties in the measured values. One way to propagate uncertainties is to use significant figures. The idea behind this approach is to round each measured value to the appropriate number of significant figures, and then carry those significant figures through the calculation. At each step of the calculation, you should round the result to the appropriate number of significant figures, based on the number of significant figures in the input values. For example, suppose you want to calculate the area of a rectangular sheet of paper with dimensions 10.0 cm by 20.0 cm. The measured value of the length has an uncertainty of +/0.1 cm, and the measured value of the width has an uncertainty of +/0.2 cm. To calculate the area, you would multiply the length and width together. A equals L x W equals 10.0 cm by 20.0 cm equals 200.0 square centimeters. However, because each dimension has an uncertainty, the final result should also have an uncertainty. To calculate the uncertainty, you would use the formula delta A equals SQRT delta L, L2 plus delta W, W2, XA. Where delta L and delta W are the uncertainties in the length and width, respectively, and A is the calculated area. Using the measured values and uncertainties, we can determine the appropriate number of significant figures for each value. The measured value of the length, 10.0 cm, has 3 significant figures, because the 0 after the decimal point indicates a level of precision. The measured value of the width, 20.0 cm, also has 3 significant figures, because the trailing 0 after the decimal point indicates a level of precision. The uncertainties, +/0.1 cm and +/0.2 cm, respectively, should be rounded to one significant figure, because they represent the precision of the measurement device. Based on these significant figures, we can determine the appropriate rounding for the final result. Because the input values have 3 significant figures each, the final result should also have 3 significant figures. Therefore, we should round the calculated area to 200 square centimeters, rather than reporting it as 200.0 square centimeters, which would imply a level of precision that is not justified by the significant figures in the input values. Using the formula for error propagation, we can calculate the uncertainty in the area as follows. Delta A equals SQRT 0.1, 10.02 plus 0.2, 20.02, x 200.0 square centimeters equals 2.24 square centimeters. Therefore, we can report the area of the rectangular sheet of paper as 200 +/2 square centimeter, using appropriate significant figures and accounting for the uncertainty in the input values. In summary, significant figures can be used to propagate uncertainties in scientific and engineering calculations, by rounding each input value to the appropriate number of significant figures and carrying those significant figures through the calculation. By using significant figures correctly in error propagation, scientists and engineers can report the uncertainty in their calculations accurately and appropriately, and ensure that their results are communicated clearly to others. Delta A equals SQRT delta L, L2 plus delta W, W2, XA, where delta L and delta W are the uncertainties in the length and width, respectively, and A is the calculated area. Explain this to me more? Break it down so I can understand it better. Sure, let me break down the formula for error propagation in more detail. First, we need to understand what the formula is trying to accomplish. When we perform a calculation that involves measured values with uncertainties, the uncertainty in the final result depends on the uncertainties in the input values. The formula for error propagation allows us to calculate the uncertainty in the final result, based on the uncertainties in the input values. The formula for error propagation that you provided is delta A equals SQRT delta L, L2 plus delta W, W2, XA. Where delta L and delta W are the uncertainties in the length and width, respectively, and A is the calculated area. Let's break down each part of this formula. SQRT, this symbol represents the square root function. It tells us to take the square root of the expression inside the parentheses. Delta L, L2, this expression represents the fractional uncertainty in the length measurement, squared. The uncertainty in the length measurement, delta L, is divided by the measured value of the length, L, to get the fractional uncertainty. Squaring this expression is necessary to account for the fact that uncertainties can be positive or negative, and we want to add them in a way that correctly reflects their effects on the final result. Delta W, W2, this expression represents the fractional uncertainty in the width measurement, squared. The uncertainty in the width measurement, delta W, is divided by the measured value of the width, W, to get the fractional uncertainty. Squaring this expression is necessary for the same reason as above. XA, this expression represents the product of the calculated area, A, and the uncertainty in the area. We multiply the fractional uncertainty by the calculated area to get the absolute uncertainty in the area. Delta A, this symbol represents the absolute uncertainty in the area. It is the final result of the error propagation calculation. When we put all of these parts together, we get the formula for error propagation. The formula tells us to take the square root of the sum of the squared fractional uncertainties in the input values, multiplied by the calculated value. This gives us the absolute uncertainty in the final result. I hope that helps clarify the formula for you. Let me know if you have any further questions. Is there anything more I need to know? Here are a few more things you may want to know about error propagation. The formula we discussed is just one example of error propagation. There are other formulas that may be used depending on the type of calculation being performed and the specific uncertainties involved. It's important to use the correct units when performing error propagation. All input values should be in the same units, and the final result should be expressed in appropriate units as well. When working with experimental data, it's important to understand the sources of uncertainty in your measurements. Random uncertainties arise from the inherent variability of measurements and can be reduced by averaging multiple measurements. Systematic uncertainties arise from biases or errors in the experimental setup and can be more difficult to account for. Error propagation is just one aspect of the broader topic of uncertainty analysis. In addition to error propagation, other techniques for analyzing and quantifying uncertainties include sensitivity analysis, Monte Carlo simulation, and Bayesian inference. Finally, it's worth noting that while error propagation can help us understand the uncertainties in our calculations, it doesn't tell us anything about the accuracy of our measurements or the validity of our underlying assumptions. These issues require careful consideration and evaluation in their own right. If you found value out of this video, like and subscribe. Please comment. Your input would be nice and suggestions are always welcome. Thanks for watching. Hope you enjoyed. Have a great day.